Welcome. In this video we start Chapter 3, Sets and Boolean Algebra, and in particular we look at Section 3.1, Sets and their operations. This is all the basics of sets. We'll see set basics, subsets, set operations, Venn diagrams, and the principle of inclusion-exclusion. Let's begin. Set basics. A set S is a collection of objects. We might say that X is an element of set S, or X is a member of set S, and we write that idea using this notation. We can write sets with the roster method. That's where you actually list the elements out. So the collection of odd one-digit numbers might be written this way. Or I can have an infinite set, say the set of all multiples of 3, As long as I'm listing out all the elements, we say that I'm using the roster method to write the set. Elements of a set do not have to be numbers. They can be results from coin flips, names of people. We can have sets of sets. And also, we can have a set that contains nothing. This is called the empty set, and we often see the empty set also with this notation, the 0 with a slash through it. And we have the universal set. Very often, the sets that we work with have some kind of a larger context. So the universal set is the set of all objects that fit that context. Some common sets of numbers are the set of natural numbers. We begin with 0 and then proceed 1, 2, 3, and so on. This is something that different textbooks will define differently. Sometimes you have a textbook that will start at 1 with the natural numbers. It doesn't really matter so long as you're consistent, and for our textbook and for this class we say that the natural numbers begin at 0. We've already played around a little bit with the set of integers. Now the set of rational numbers, that's the set of all fractions that look like a over b, where a and b are integers, but we don't allow b to be 0. And then R, the set of real numbers, that's just everything on the real number line. If A and B are sets, then containment is indicated this way. I write A, it looks like a little C with a line underneath it. That means that every element of A is also an element of B. I write A is contained in B, or A is a subset of B. So take a look at these problems 1 through 6 and see which are true. Give this thing a try. Pause the video and unpause when you are ready to check your work. Alright, let's take a look. False, true, false, true, true, false. A couple of the tricky ones are 4 and 6. Number 4 says that the empty set is a subset of ABC. And that's kind of weird, right? Well, any element that I take from the empty set, is that in the set ABC? It kind of is, because I can't really take any element out of the empty set. It turns out that the empty set is a subset of every set. The other tricky one is number 6. And you might think that this is true because I see an A and a B on the left, and I see an A and a B in the right, but A itself is not an element of the set on the right, and B itself is not an element of the set on the right. Now, I could make this into a true statement if I had actually used the element symbol. So it turns out that it is true to say that the set AB is an element of the set on the right. Set builder notation. So this is a compact way to describe large sets. This is an alternative to roster notation and more powerful than roster notation. There are two ways to write set builder notation. One focuses on the property of numbers and the other focuses on the form of numbers. So for example, both of these sets here on the right show the same thing. The first one says the set of all n in my integers such that n is divisible by 4. So something like negative 8, negative 4, 0, 4, 8, 12, and so on. The set of all integers n such that n is divisible by 4. There we go. Another way I could express that is the set of all things of the form for k such that k is an integer. So either way I say it, it gives me the same result. So take a look at these four problems here, these four sets. These are sets listed using the property description. And see if you can come up with three members of each of the following sets. Here, I'll read them out loud. Number one, the set of all natural numbers n such that n is an even perfect square. Number two, the set of all x in my set of integers such that x minus 1 is divisible by 3. Number three, the set of all rational numbers r such that r squared is less than 2. And number four, the set of all x in my set of real numbers such that the sine of x equals 0. Pause the video for a few moments, write a few elements out for each of these sets, and then play again when you are ready to check your work. Alright, let's take a look. Number one, the set is 0, 4, 16, 36, 64, 100, and so on. So I've written it out in roster notation. Number two, there it is in roster notation. Number three, this really turns out to be any rational in the open interval from negative square root of 2 to positive square root of 2. And number four, these are all the x values where sine of x equals 0, which is exactly the integer multiples of pi. How about the form description? So number one says 3n squared such that n is an integer. Number two, 4k plus 1 such that k is a natural number. Number three, 3 minus 2r such that r is a rational number and r is between 0 and 5 inclusive. Can you find three members for each of these sets? Once again, pause the video for a moment, give this thing a try, and then start it up again to check your work. Alright, let's do this. There is the roster form for the first set, roster form for the second, and for the third set, it's going to be any rational number in the closed interval from negative 7 up through 3. Now, how might you write this thing using set builder notation? Again, pause and try. See what you can do. There's more than one right answer, so see what you think. Alright, so here's one way I might write it. 2n plus 10 such that n is a natural number. Do you see? So I think my n kind of starts off 0, 1, 2, 3, and so on. And then for each of those n, I plug it into the formula, 2n plus 10, and I'll end up with the numbers 10, 12, 14, 16. So this is the form version. Here's another way. How about something like 2k, such that k is an integer and k is greater than or equal to 5. So my k values really start off 5, and then they go 6, 7, 8, 9, and so on. And for each value of k, I'm going to double the k. This form isn't really the form version or the property version. It's somewhere in between. And then here's one with the property version. The set of all a such that a mod 2 equals 0. In other words, a is even. And a is greater than or equal to 10. That could be another way to express this in set builder notation. Now we move on to set operations. In the same way that we can take numbers and add or subtract them and come up with new numbers, we can do operations on sets, where I combine sets together to get new sets. So consider the set A, which is 1, 2, 3, set B, which is 3, 4, 5, and both of these sets live in the universe, which is the numbers 1 through 10, the integers 1 through 10. So I can intersect two sets. The set of elements in both A and B is A intersect B, and in this case it is the set containing only the number 3. 3 is the only number that is common to both A and B. The symbol for intersection looks a little bit like the symbol for logical AND. It's just a curvier version. And that's not a coincidence, because the intersection is the set of elements in both A and B. Now, union is when I put two sets together. It's the set of elements in either A or B. Once again, I have the OR, and the symbol looks like a curvier version of the logical OR. So what are the set of numbers in either A or B? It's 1, 2, 3, 4, and 5. So those are all the numbers in either A or B. I can do a set minus, one set minus another. The set of elements in A which are not in B is A minus B, In this case, it's the set containing only 1 and 2. I start off with my set A, and then I take away anything that happens to be in B, which in this case is only the number 3. And then complement. The set of elements in the universe which are not in A is A prime. So not A. And in this case, A itself contains 1, 2, 3, so A prime, or A complement, is 4, 5, 6, 7, 8, 9, 10. So here's some practice with set operations. You'll see sets A, B, C, and D defined, and we'll continue to use the universe, that is the integers from 1 to 10. So for each of these 10 problems, give them a try. Like before, pause the video, really take some time, see if you can figure out these set operations, and then when you're ready, start up again and check your work. Alright, and the solutions are all right there. I'll just leave them up. You can pause if you want to check your work and see how you did. Alright, let's move on. Venn diagrams. Venn diagrams are a nice way of visualizing subsets. I will go to this website now. So in this activity, I can click on various portions of the graph and get different subsets of the sets. I can even click on the area outside of all the sets, but still within the universe. So right now it's asking me to shade in what represents set C. So there we go. Those are all the elements that are in set C. Very good. Now how about A complement? How would I shade that? So that's everything not in A. It's tempting to think that that is A complement, but not quite. I need more. In fact, I need everything in the universe that is not in A. How would I indicate A union B? Let's try shading in all of that. So there's the visual representation for A union B. A intersect B, so this lens-shaped region. Let me move on here a little bit. B prime, C prime. How about this one? A complement intersect B. Can you see what that'll be? A complement intersect B. So A complement means everything not in A, so everything outside of A, but also it has to be in B. So I'll start with the A complement. Here's my A complement, but I don't want everything green. I only want that green stuff that's also in B. So in fact, I think it might look like that, sort of the crescent moon-shaped object, right? Let's try another one. How about A intersect B intersect C? Maybe that's the region just right in the middle there. And one more. How about A union B complement? What do you think that'll be? Can you visualize that before I shade the region in? A union B complement. Now the parentheses tell us let's figure out A union B first, and then whatever I end up there, then I'll take the complement of that. So A union B, here I'll just actually shade that in first, that's A union B, that's the stuff in the parentheses, but then I want the complement of that. Alright, so how about the universe together with some of that other stuff? Alright, so that's just a quick demonstration of visualizing sets and subsets using Venn diagrams. And this brings us to our last topic, the principle of inclusion-exclusion, or pi. Okay, so quick notation here. N of A means the number of elements in set A. So if I have a set that with 5 elements, so for example A is 2, 3, 6, 8, 9, then N of A equals 5. We sometimes say this is the number of elements in A, or the cardinality of A, or even the size of A. So here is the principle of inclusion-exclusion with 2 sets. The number of elements in A or B, sort of the number of elements in A union B, is the number of elements in A plus the number of elements in B minus the number of elements in both A and B. That is the number of elements in the intersection. So why should that be? Well, look at this. If I'm trying to work this out, I want to know how many dots are in this picture. That's the size of A union B. I would first count all the dots in A, and then I might count all the dots in B. But look what's happened. I have overcounted the stuff in the middle, in the lens shape that is the intersection of the two. Since I've overcounted the stuff in the middle, I need to subtract off one of those. And that will give me the correct counting. So I overcount a little bit, and then I subtract off to make my count correct. Here's an example we can do that uses numbers. Set A is the set of all multiples of 2 up to 100. Set B is all the multiples of 5 up to 100. So how many numbers are in both of those sets all together? And I don't want to count repeats. So the number of things in A union B is the number of things in A plus the number of things in B minus things in both A and B. So what is the size of set A? What's the cardinality of A? Well, the even numbers up to 100, that's 50. And the number of things in B, well, all my multiples of 5 up to 100, there's 20 of those. Maybe this one's a little bit trickier. How many things are in A intersect B? Well, what do they have in common? I guess it's really just multiples of 10, right? If I were to write out the 10 there, I'd see 10 and 10 is common to both. And certainly 20 and 20 would be common to both. And 100 and 100 is common to both. So, yeah, so it's what's common to both the intersection is really just the multiples of 10. And there are 10 of those up to 100. And so that gives us 60. So the answer is 60. There are 60 unique numbers that are either multiples of 2 or multiples of 5 up to 100. Here's a slightly more complicated situation. What if I have 3 sets? Principle of inclusion-exclusion for 3 sets is a little bit similar and a little bit different. I start the same way. I'm going to add everything in set A plus everything in set B plus everything in set C. But I've done some overcounting. So I'll subtract off the things that are common to each pair of sets. I'll subtract off the number of things in the intersection of A and B. I'll subtract off the things in the intersection of A and C. I'll subtract off the number of things in the intersection of B and C. But then it turns out I've subtracted too much, and this most central part has actually been subtracted too many times. So then I need to add that back in. All right, let's see how that works in an example. A, like before, is the set of all multiples of 2 up to 100. B is the set of all multiples of 5 up to 100. And now C is the set of all multiples of 7 up to 100. How many things, how many numbers are in A union B union C? Go ahead and pause the video, see if you can work this out. Start up again when you are ready to check your work. Okay, so individually, the number of things in A plus the number of things in B plus the number of things in C is 50 plus 20 plus 14. Now, A and B together have 10 elements. A and C, that is the multiples of 14, have 7 elements. And B and C, so that's the multiples of 35, have only 2. The only elements in B intersect C are 35 and 70. And then I add back in the number of things that are common to all 3 sets. And what is common to all 3? Well, there's only one number, that's actually the number 70. And so doing the arithmetic, we end up with 66. All right, we've covered a lot. We've hit all the basics of sets today, and that brings us to the end of 3.1.